So our next topic is conservation of energy. So the goal today, I can explain the conservation of energy and make the connection between gravitational potential and kinetic energy in a closed system. So, law of conservation of energy, extremely important here. It's going to play a massive role in grade 12, and it's going to play a massive role for us in the next couple of the next week or so. So the law of conservation of energy states that energy cannot be created or destroyed, but simply changed from one form to another. So no energy is lost. So energy is continually changing from one form to another. So this begs the question, when I had the roller coaster in the previous lesson, we found a location where gravitational potential energy was zero. Where did that energy go? So let's take a look at this example kind of to illustrate that point. So we have a falling rock 10 meters above the ground. So scale ground. So here's 10 meter mark, here's the 5 meter mark, and then 0 meters. So I'll draw a picture of the rock. Okay, so there we are. It's falling down. Let's track its energy. Okay, let's track its energy. At the top, gravitational potential energy. Let's start with that. So that would be mgh, and for the purposes here, I'm going to work sideways. There'll be math teachers that are kind of freaking out a little bit, but we're going to work sideways just because it looks pretty. All right. So the mass of the rock is 10 kilograms, gravity 9.81, and the height is 10. And like I said, I'm working sideways for this example only. Please do not do this in your solutions. So we've got 100 times 9.81, so that's 981 joules. Let's leave some space, and now we do gravitational potential energy here, which is mgh. So that'd be 10 kilograms, 9.81. Now it's at 5 meters, and now it's going to be half the energy of 981. So divide that by 2, so we get 490.5. Finally, at the bottom here, mgh equals 10 kilograms, 9.81, 0 for a height, which means it has no GPE, so it's kind of like the roller coaster. All right, now let's talk about the rock, or the kinetic energy. So kinetic energy, EK equals 1/2 mv squared. When this rock is at 10 meters, and we're just about to drop it, it has no initial velocity, okay? So it has no initial velocity, so it would be 1/2 times 10 times 0. So it has no kinetic energy at that point. If that's all the energy that's involved here, then the total energy of the rock at 10 meters is 981. In between, we got to find our EK. So 1/2 mv squared equals 1/2 10. Now I need to find that velocity there. And at the same time, just going to kind of kill two birds with one stone, so to speak. 1/2 times 10. I need to find the velocity there. So how do we find that velocity? Well, off to the side, we've got to do some calculations. We're going to have to use our kinematics formula. All right. I know displacement. I know initial velocity. So I'm going to use my v2 squared equals v1 squared plus 2ad. That's d. So in both cases, the v1 squared is 0. So I'm going to work, like I said, I'm going to do both of these at the same time. So that would mean that my velocity at this point is 2 times 9.81 times 5 meters. I need to take the square root of that. So at 5 meters, it's fallen 5 meters times 5 square root. I get 9.9 meters per second. 10 times 9.81, just going to double check that, 9.9. At the bottom, so again, I'm going to have to take the square root of both sides. So square root of 2 times 9.81, and it's fallen 10 meters at this point. So 2 times 9.81 times 10 square root, I get 14 meters per second. So now I have the velocities at both points, so then I can do some calculations. So 9.9 squared, so 0.5 times 10 times 9.9 squared. I get 490.1. And at the bottom here, if I put 14 in, 0.5 times 10 times 14 squared is 980. And everyone is gasping in horror as they realize that if you add that up, that actually gives you not quite 981, but close enough for my liking. So that's 981. And at the bottom, 980. Sure, 981 because I'm rounding off here. So look at that. No matter at what height we are with the rock, it has the exact same total energy. Has the exact same total energy. Is the energy in the same form? No, it's all gravitational potential. It's now split halfway, and now it's all kinetic energy. So the energy form transfers from one to the other, but the total energy within the system remains the same, remains constant. So I'm going to put the formula on the next page. So as a formula, energy in the system is equal to gravitational energy plus kinetic energy plus mechanical energy, so that's work, so I'll put that W above just as a reminder, plus, what else do we have? Well, chemical energy from chemistry. We could have thermal energy from heat, plus dot, 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 dot. So energy is always the sum of those energies, okay? So in terms of the roller coaster, all right, if I sketch out my roller coaster, again, if I know that my energy total, so ET, if ET is equal to 1,000 joules here, that means down here, ET is equal to 1,000 joules, which means right here, it's equal to 1,000 joules. Now, we're going to lose thermal energy to friction in the tracks, etc., etc. So in a real world, in our world, it's not always going to be 1,000 joules, but in physics, we assume ideal conditions. We assume that we're in a perfect world. So that's true all the way through. So conservation of energy within a closed system remains the same. So that's the roller coaster. The other one I wanted to talk about quickly here is a bouncing ball. All right. So if we bounce a ball, goes to the ground, what happens to the ball? It bounces up, but it doesn't bounce as high. So it decreases in height every time after every bounce. Why is that? The energy conservation of energy law says that no energy is lost. It's just transformed into one form or another. So where is this energy loss occurring in terms of the gravitational potential? Okay. Well, energy is transformed into, so GPE, gravitational potential energy, some of the energy forms. If you drop a ball, what do you hear? Well, you have sound energy. In order to have sound, there must be some energy spent, and there will be some heat energy from the compression of the ball. So a bouncing ball still follows our law of energy conservation. It's just being transformed into undesirable energies. And I would really like my ball always to bounce to the same height. Sound, I don't really care whether I get sound. Heat energy, same thing. It's undesirable loss, but it's still, that total energy is still there. So the total energy in this system for the bouncing ball would be your gravitational energy plus the energy now that's gone to sound plus the energy that's gone to heat and everything else. Okay, so energy remains constant even though you don't think it is. You just got to figure out, well, where did that energy get transferred to? So that's a bouncing ball. All right. So a couple of examples. I'll run through with those. How about I just split the difference? I'll just do it in the next video. I'm going to have to go into the second one anyway. And we'll move on from there.